Dear students, welcome back to Architecture and Programming Models for GPUs and Coprocessors. Today we're again going to talk about CUDA and about GPGPU. While last week we had more of a general overview, today is going to be a bit more hands-on and we will see some more actual code and we will learn more about the general programming concepts of the CUDA API. So, as an outlook to how the lecture will proceed, after we have finished our discussion of CUDA and of GPGPU, we will then talk about applications, and in particular, in the last part of the lecture, we will learn how to write sorting algorithms on GPUs. So last time we already started talking about CUDA and about the CUDA single source model, where we were able to have both host and device functions in the same CU source files. And we'll now have a quick look at how this is actually handled by the CUDA compiler, by the NVCC compiler. And all this is assuming that we're using the CUDA runtime API, and the CUDA runtime API has this peculiar notation here where we have those three angle brackets. And the angle brackets are special syntax, and the special syntax tells the compiler that we are calling a CUDA kernel, so that we're calling from the host that we're calling a device function. And then we have the device function, like we have the kernel, which is the global entry point on the GPU. And like we can have a bunch of them actually, as opposed to on the CPU, where we are only allowed to have a single function main per application. We can have multiple such entry points, like such kernels, and we would call our kernel, and potentially the kernel would even be located in the same source file that the host code is located in. And then from within the kernel, we can call functions, but those functions need to be device functions. So only functions that are annotated with device can be called from the kernel, and functions that aren't annotated, or functions that are annotated as host functions, they can't be called from within kernels, so they can be called from within the device. Then there are also certain other functions which are marked both host and device, and those functions are compiled for both the host and the device, and the device version of this function is also callable from within the kernel. So and now the CUDA NVCC compiler needs to figure out which code to compile in which way. Like the instruction set architectures that are used for the host functions and for the device functions are just very different, right? So on the one hand, we might have an x86 or an ARM instruction set, while on the other hand, we have this CUDA machine code, and we have this intermediate representation that CUDA device code is compiled into. So the NVCC compiler will take our source file and will run a pass over that source file to identify which of the code goes to the host compiler and which part of the code goes to the device compiler. So, and the host compiler first needs to be patched. Like, the host code is really basically just C++, with the only exception being this special function call syntax here, where we call into the kernel. So the NVCC compiler will now patch the host code and replace the function call syntax, like the kernel call syntax, with a special patched code, and that patched code basically comes from the second host API that I briefly mentioned, like from the driver API. And the driver API is a real C API, where there's no extra syntax. So the host code will be patched so that those kernel calls become real C calls. And this is basically it. And this patched code is real C code and can actually be compiled by GCC or by the Microsoft compiler or whatever host compiler you use. And this is actually what NVCC does. Like, NVCC will dispatch the patched host code to the host compiler, like to the host compiler that you configured. So you can tell NVCC which host compiler you're compiling with. So that leaves us with the device code, and the device code is compiled into an intermediate representation, and the intermediate representation is called PTX. Like, the intermediate representation can be thought of like a bit as of like Java bytecode, or as the intermediate representation that the CLang compiler would create, Like it's a intermediate representation that is pretty similar to actual machine code, but it is missing certain specifics underlying the actual machine that we're running the code on. So we have a assembly-like language that the device code is compiled into, but the assembly-like code in this intermediate representation isn't optimized yet for the actual machine that the code will later run on. So what we're now basically have done is we have resolved the runtime API part of the CUDA execution model. So what we're basically left with is with code that we would also have used or generated with the CUDA driver API. So with the CUDA driver API, you would have those C functions that are on the host side, and then you have PTX code. And this PTX code can be interpreted by the driver, and the driver will figure out which GPU you're running the code on. Like we're now really at runtime, because all this here happens when your program is compiled, and now we're actually running our program, and the PTX code is handed over to the driver, and the driver can figure out which GPU we're targeting, and will create actual machine code from the PTX code. Like the driver will also usually cache that code so that when we execute the application for the first time, it takes a little bit to compile the PTX code into machine code, and then it will usually cache that code. So the patch host code, as I already said, is compiled by your host compiler. So this is the blue box where we're still in compiled mode. And then we end up with some like object code, and the object code is basically just a CPU program, and that CPU program can call the machine code and can directly call the machine code using those C API functions here. So the compilation model is basically a mix of a real compilation model and a just-in-time compilation model, as in that the device code is first compiled to PTX, and that happens at compile time. And then we have the driver just-in-time compiling the PTX code. And then there is something that NVIDIA calls QBin, and that basically just means that when we compile our PTX, then we can instruct the NVCC compiler to output a so-called QBin file, and that QBin file actually contains the PTX code. And with the QBin file, we can not only inspect the PTX code, but we can actually patch it, and if we desire so, then we can actually manually optimize that PTX code. So PTX and the overall machine model of CUDA is either 32-bit or 64-bit. And whenever you write a 32 or 64-bit application, that means that both the device side and the host side are 64-bit. And we will later also learn about what is called a device pointer, which is basically a pointer that lives on the host, but that references memory on the device. So we can have pointers, and we have access to those pointers, like we shouldn't dereference them on the host, but we have access to them on the host. And it's now important that host and device agree upon the size of a pointer, for instance. Like if the host thinks that a pointer is 64-bit and the device thinks it's 32-bit, then it's a problem. So CUDA doesn't even allow us to have separate bit widths per device and per host. So our application is either a 32-bit or a 64-bit application, and usually when we're on a 64-bit system, then NVCC will make sure that our whole toolchain compiles in 64-bit mode. The execution model inside the CUDA kernels, and the execution model that is also reflected by the PTX code, is what NVIDIA calls ZIMT. Like this is of course inspired by ZIMD, and the acronym actually means a single instruction multiple thread, and basically reflects that inside those kernel functions we have individual threads, but those threads execute inside a warp, so in a thread group. And this is the execution mode that NVIDIA calls ZIMT. And so what distinguishes this from ZIMD mostly is that there are no ZIMD opcodes. So when we look inside the PTX files, or when we use CUDA objdump to inspect the SASS code that will be generated from the PTX, then we will see that there are no vector instructions. Like there are no ZIMD instructions and no ZIMD opcodes, but the registers and the instructions that are used, they are all scalar. And the execution model still implies a lockstep within verbs, but the instruction set is not a SIMD instruction set. This is opposed to other GPU vendors like AMD, at least for certain architectures, has real SIMD opcodes and has real SIMD instruction set architectures. So with NVIDIA, this is implicit. So we have those verbs, but there's not like a single instruction executing on the verb, but instead the verb just executes on a lockstep. So that means that we have this thing when that when the verb encounters a branch, then a single thread can cause the whole verb to wait at that branch. So and when we run our kernel, that is when we use this peculiar function call syntax with the angle brackets, this will cause the GPU to spawn as many threads as there are threads in the grid that we configured when we set up our grid of blocks and when we told CUDA what the block size actually is. So when we do this, CUDA will call those kernels and will spawn threads, and we will now have a look at how those kernels are actually programmed, like what real-world kernels would actually look like. So now we're gonna look at some real CUDA code. Like the kernel call syntax we're now already familiar with. And we have our kernel, which is annotated with the keyword global. And we also have this function call syntax with the angle brackets. And inside those angle brackets goes the number of blocks of our grid and the number of threads per block. So here's a few examples of how those kernels could be called. Like imagine we have this ZaxP kernel, and as you can see, the kernel is just an ordinary C function, and the kernel can also take parameters. Like the kernel can take a parameter A here, which is just a scalar, and where the parameter is actually copied into the kernel by value. And then we have two pointer parameters, and those pointer parameters are also copied into the kernel by value. And those pointers are so-called device pointers. So that means that we have to make sure that the data that we pass into those kernels actually lives on the device. So and the pointer will point to some memory region that is accessible from within the device. So that way when we dereference that pointer, like where we use the array notation to access the array X, we have to make sure that this data actually lives on the device. And you can see that the data can be modified, so we can both read from those data arrays and we can actually also write to them. So, and you see a very simple kernel here, and in that we only have a single block. So this is a one-dimensional kernel, and the one-dimensional kernel has a single block with n threads. So the two variables that go in here, like the number of blocks and the number of threads, are of type dim3, so they are vectors actually. And in the trivial case that we have a 1D grid, we are actually allowed to also use this syntax here. And this kernel is really very trivial because on CUDA architectures the number of threads per block is limited. So we can have large grids, but the number of threads that are in a block is actually limited. Like I believe that in certain architectures the limit is 1024. So like the limit is like in that ballpark. And that also limits the size of the arrays that we can actually work on here. And in this very simple case where we only have that single block, we can now identify the data item that each thread is responsible for by just querying the local thread index. This is what we're doing here. So, and assuming that the maximum block size is 1024, then the maximum vector size of those x and y vectors here is 1024. So a similar kernel that does something else that actually operates on a 2D grid would look like this, where we again have a single block and where we have n by n threads. And again, those n by n threads may not exceed a certain limit, like the limit usually being 1024. So we're now calling our kernel here, and we're calling our kernel with a 2D configuration. And that means that the thread index x and the thread index y variables are now set. Like in the kernel, the thread index is always a three-dimensional variable, but if we call a kernel with a configuration that would be 1D, then thread index y would always be 0, so it wouldn't make sense to actually access it that way. And as you can see here, I also have a data domain that is two-dimensional. Like we're accessing a matrix here, and we're performing a matrix-matrix addition here, actually. Like we're accessing the two matrices A and B. Then we're adding them component-wise and storing the result in C. And we're doing this only for a single block, and there's again this upper limit for the block size, so the size of the matrix is severely limited. So if we want to make this scale to arbitrary matrix sizes, then we have to use more blocks. And so here's an illustration of that. Like suppose we're adding those two 5x5 matrices. So as of our example, n is 5. And we're using 4x4 threads per block. So our block dimensions are 4 in the x direction, 4 in the y direction. So then we have this roundup method, and the roundup method helps us to compute the grid size. And the grid size is just n over the number of blocks, so 5 over 4, and that rounded up. So that gives us the grid size of 2 by 2. So we now have a 2 by 2 grid, and as you can see, the dimensions of the matrix aren't exactly divisible by the number of threads per block. And therefore, we have what I call the halo, like this area here, where there are threads that aren't assigned any actual work. So in order to extend our example a bit, like the example from the slides, like this is just replicated how those global matrix indices would be calculated. So in order to extend our example a bit so that it also supports matrices of arbitrary dimensions, we would have to make sure that threads that are allocated to those halos don't perform any work and exit immediately. So and that's what we're doing here. Like this function matrix add now computes global instead just local thread indices. And when we set up that kernel and when we call that kernel, we allocate a grid that has enough blocks to accommodate the whole matrix, like a matrix that is bigger than, in this case, 32 by 32. And in order to accommodate matrix dimensions that aren't divisible by 32, we use this roundup function. And then for simplicity, I omitted the handling of halo threads here. Like for an example that would actually work with matrix dimensions that aren't divisible by 32, I would have to include some halo handling here that would reject the I and j indices if they're inside the halo, so I would have to implement some basic bounds checking. And this is generally how one would implement a 2x2 CUDA kernel call using the grid metaphor. So we now have a fairly well understanding how this grid metaphor works. And in the following, I'm only gonna repeat a couple of things that we already discussed. Like we already discussed the occupancy calculator. And we know that the occupancy calculator can help us to compute the ideal block size. And the ideal block size depends on the registers that are used by the kernel. And in order to find out how many registers our kernel uses, we have to pass a compiler option to NVCC, and in particular we pass this compiler option ptx-as -v, like the -v means verbose, and ptx-as is the assembler, actually, is the ptx assembler. And if we call NVCC in this particular way, then it will report certain statistics about the kernel that were just compiled. Like here's some example output from ptx-as. When you're passing the -v, the verbose option, it'll then tell you the name of the kernel that was compiled, like in this case, I see that the kernel was just called kernel, and that I compiled the kernel for the SM20 compute architecture. Like, this is a flag that I also can pass, and it will then tell me that there were no registers that were spilled to local memory. I can see that the overall register use is 20, and I can also see how much constant memory is used. And in this case, I don't use any shared memory at all, but if I used shared memory, then the report would also tell me that. And then I would use those statistics and would enter them into the occupancy calculator that we saw in the last session, and the occupancy calculator would tell me the optimal block size based on this static code analysis. So in the following, we will just repeat certain things that we actually already know about kernels. Like, we already saw how global thread indices are computed, and we know that there are grids that we allocate in order to allocate threads, and we know that the grid has up to 3 dimensions, and I can specify any of those dimensions, and implicitly, when the grid size in one dimension becomes greater than 1, then I have a 2-dimensional or a 3-dimensional grid. And when I set like the second dimension or the third dimension to 1, then the grid size is just, the grid dimensions are just 1D or 2D. And then in the kernel, I have those variables available, like the block index and the block dimensions and thread index. And I also have the grid dimensions actually available, so that I don't have to compute them using a division. I also know the actual grid dimensions. And I can use those variables, like I can access them from everywhere on the device, like whenever I'm in device code, like when I'm in a kernel, but also when I'm in a function that was called from within a kernel, then I have access to those global variables, and they will tell me how the kernel was called, and will tell me the current thread index, and I can compute the global thread index from that. So, like, this is also just repetition. The CUDA kernels follow the single source model, so I can just combine host and device code. And then in particular, I can actually even have a kernel being a class member function. So I can have like a class, and the class is maybe a host type, and then the class contains a member function that is just the CUDA kernel. So there's all sorts of ways that I can mix host and device code actually. And in the kernel, I can use pretty much everything from C++, but for certain dynamic features, like in particular, dynamic memory allocation is something that I cannot use, like I cannot call malloc or free. But I can in general not use any library functions, like any host code cannot be called, and I can in general not use any library functions. And as a matter of fact, certain library functions, and in particular math library function like cosines, sines, also certain other POSIX functions are actually implemented as device code and are shipped with CUDA. So in particular math facilities, or also certain POSIX functions, they can just be used from within the kernel when I include the appropriate header, and this also includes functions like, for instance, printf. So there are certain functions, C functions, that I actually can use, but this is due to the fact that there are dedicated implementations. Like, we'll find more documentation on this in the programming guide, but in general, it's not possible to call arbitrary library functions from within CUDA code. Certain library functions are exposed though. So, and then other features that cannot be used from within kernels are like recursion can only be used to a certain degree. Like, there is a limited support for recursion. Virtual inheritance, etc. Certain things are exposed by certain architectures, and by others they aren't. And in general, those dynamic. And when it comes to runtime type identification facilities and your code being dynamic about what a type evaluates to at runtime, those features are problematic or ill-supported with CUDA. As said, there are those annotations that allow me to tell CUDA if a function is compiled for the host or for the device or for both. And just to be explicit about this, like, here are 4 tiny functions, and all of them compute a vector dot product. And the first function is a host-only function, like this function was only compiled for the host. The second function is a host-only function too, because it's annotated with host. So the third function is a device function, so can only be called from within a kernel or from within another device function. And then finally, the fourth function is a host and device function, and then this will mean that NVCC will actually generate two versions of this function. One version that is callable from the host and the other that is callable from the device. One other remark about device functions, so those functions that are called from within a kernel, is that they are usually inlined by the compiler. And that actually has a reason, and the reason is basically scarceness of GPU registers. Like when you recall how a typical function call is implemented on the host, on the CPU, that would involve several registers. Like there are certain special registers for passing arguments to the function. Then there are special purpose registers like stack-based pointers. And this stack-based pointer would be used to temporarily store the address that the function will return to when it's executed. And all this is of course quite register intensive, and for those reasons the typical function call mode on the device is actually inlining, where the compiler will just perform text replacement inside the compiled file. And there are exceptions to this, like there's a so-called CUDA separable compilation mode, where it's actually possible to call into functions from a different CUDA compilation unit. This is actually relatively slow, like when you use it, you will find that it's relatively slow when you do this in inner loops. So the default mode is actually inlining, with very few exceptions that might make sense in certain cases, and in others they actually just don't. So we now learned the most important things about CUDA kernel code and about the code that actually runs on the GPU, and we see that the GPU device-side language is C++ with a few exceptions, like certain features that aren't supported, certain language features that were added, like those special variables that are available, like special annotations for function calls for device functions. And this is pretty much it. We will, in the following, encounter more device code and more code that is used inside kernels. In general, there are a few best practices that I want to briefly mention when you write device code. And I'm sure there are a bunch more of them, but those are the ones I personally find the most important. And the first best practice that I would recommend is that when you're in kernel code, then you always have to be aware of that your kernel code isn't run by only a single thread in isolation, but there are like a bunch of threads that execute that code at the same time, simultaneously. And therefore, and in particular regarding the way that threads are executed, that they are grouped into works, it's important to be aware of issues that arise when the code diverges and when there is dynamic branching. A second best practice is, like in contrast to host code, memory accesses have an extraordinarily high latency. This is important to keep in mind, and quite often it's worthwhile to perform extra calculations in favor of extra memory accesses. So quite often it doesn't actually pay out to store something temporarily in our DDR memory, but instead recomputing it over and over again. Another important best practice is to avoid costly back and forth between CPU and GPU. So as soon as your data is on the device, then you should try to keep your control flow on the device. And switching between CPU and GPU, and in particular if this involves copying data around, is extremely costly. So this is something that you should keep in mind, and quite often it's worthwhile to restructure one's code so that the code can actually stay longer on the device and doesn't return execution to the CPU, and in particular doesn't require any copies from the GPU to the CPU or the other way around. So with that knowledge about the device side language of CUDA, we were now going to discuss the host side part of CUDA, which manifests as the CUDA runtime API. So we'll now start with a discussion of the CUDA runtime API. And anyway, as the two languages, like the device-side language and the C++ C runtime API, are pretty much linked, we'll also encounter and discuss device code in the following. But we'll now concentrate on the runtime API. And the runtime API basically just manages the interface between the host and the device. So the runtime API is comprised of a bunch of C functions, and those C functions, they can be identified by their prefix, like all those functions are identified with the prefix CUDA, like for instance CUDA malloc or CUDA memcopy or free. And there's also the driver API that I briefly mentioned, and the driver API is also a C API, and those functions also have a prefix, like a common prefix CU, so the prefix CU can be used to identify the driver API. So the driver API has prefix CU, and the runtime API that we will concentrate on in this lecture has the prefix CUDA. So, and the driver API, as already said, has a notion of a context. Like we discussed contexts also when we talked about OpenGL. And CUDA contexts are actually quite similar, only that they're like not associated with a single thread, like OpenGL had this notion of one context per thread. Well, with CUDA, we just have one context, and all CPU threads actually share that context. And with the driver API, this is explicit, like there is a CU context object, and that a CU context object needs to be initialized, and it needs to be maintained and managed by the user. And with the runtime API, the context is also there, but it's implicit, so the user never gets in touch with the context. So what actually happens is that whenever we call a CUDA runtime function, like the very first CUDA runtime function will try to initialize the context. So if there is no context, then the first call will implicitly cause the API to initialize the context, and then when the next runtime API functions are called, the runtime will just figure out that the context was already initialized and will not initialize it again. And there's also a function that is called CUDA device reset, and the device reset internally will destroy the current context, and the next runtime function that is called right after will try to create a new context. So with CUDA, all this is implicit. Most of the CUDA runtime API functions return an error code. So whenever we call a CUDA function from the runtime API, it'll return an error code. Like there are a few exceptions to this. And we also talked about certain functions with the CUDA API running asynchronously. Like in particular, kernels can run asynchronously depending on how they are called and how they are set up. And in those cases, we also might encounter asynchronous errors. Like in particular, CUDA kernel calls can also cause CUDA errors to happen. Like for instance, when a kernel performed an illegal memory access, this will result in a CUDA error. So when I have a CUDA kernel that runs asynchronously, that means that an error is generated asynchronously, and it's kind of hard to tell who actually generated that error. And CUDA has those functions CUDA get last error, and also the function CUDA peak last error. And those functions, they let us check errors from CUDA calls. And the only thing that we have to be aware of is that certain functions are run asynchronously and can also create errors. Like this might in particular result in the last error not being the actual last error. And in order to debug this better, there are synchronization primitives that we can use, like in particular the function CUDA device synchronize, and the CUDA device synchronize function is basically a barrier. Like when we call a CUDA kernel, then we can ask via the function CUDA get last error if there is an error that was generated by that function. And when kernel calls are allowed to run asynchronously, then it is good advice to not use the CUDA get last error function actually, but to use the CUDA device synchronize function. And the CUDA device synchronize function will basically cause a barrier synchronization to happen and will return the last error from the previous kernel call. So this is something that you would usually only do in a debug scenario, because this will slow down your code. But it is important to be aware of that CUDA kernels can cause errors, and those errors usually happen asynchronously while the CUDA kernel runs. And when there's something happening in the meantime while the CUDA kernel runs, then we have to make sure that the device is appropriately synchronized so that we actually catch that error. And then in certain cases, like when we actually have overlap, then it's actually pretty hard to debug where a CUDA error actually manifested from. So the CUDA functions themselves can return error codes, like the memcopy function, for example, returns an error code. And this error code might tell us something about like the memory transfer not being successful. And at the same time, we also have lots of asynchronous like kernels, and there are other asynchronous functions too. And those can also cause errors, and we have to make sure that whenever we perform error handling, that we actually know where the error comes from. And in particular, when we're trying to debug our code, then we have to make sure that kernels and other functions are sufficiently synchronized. So the first thing that we are going to discuss is global memory management. That is how we allocate and how we free and how we manage GPU DDR memory. So memory that is accessible from the device. And CUDA global memory management is done using so-called device pointers. So what we basically obtain is a C-style raw pointer. So here in the example, I'm declaring a pointer, like a pointer to integers. And this pointer can be initialized as a device pointer using the function CUDA malloc. And the CUDA malloc function is similar to the malloc function on the device. Like the calling semantics are a bit different in that the CUDA malloc function won't actually return the pointer, but is passed an address to the pointer. And then I tell CUDA malloc the size in bytes that the allocated memory region has. Like in this case, I'm just allocating enough memory to hold 32 integers. And then I have this device pointer, and the device pointer is visible on the host, so all this here is host code. But if I would dereference that device pointer on the host, there would be a memory access violation, because the address that the pointer points to is not within the address space of the host, but within the address space of the device, which just has a different address space. So we cannot dereference that pointer, but we have it available on the host, and we can actually also pass it around. So we would later be able to pass that pointer into a CUDA kernel as an argument. So if we had a CUDA kernel that would take pointers as an argument, we would pass that device pointer into the CUDA kernel, and inside the CUDA kernel, that is when we're on the device, we're allowed to dereference that pointer. So, of course, whenever we call malloc, we also have to call free. So in this regard, the semantics of malloc and free are the very same as their host equivalents. So, and when we have obtained our device pointer using CUDA malloc, then we can move data around. Like, what that involves is always that we have data on the host, like here in this case the host array. And the host array just holds a bunch of integers. And here in the example, I'm calling malloc that can hold the exact same number of integers on the device. So now I have my host array and the device array, and then I use CUDA memcopy to copy from the host array to the device array, and I tell it how many bytes to copy, because CUDA memcopy, the very same that the NVCC memcopy function isn't aware of types, the CUDA memcopy function is neither. And I tell it how many bytes I want to copy, and the CUDA memcopy function does just that. So, and as a matter of fact, the CUDA memcopy function is a bidirectional function, in that I have to tell CUDA memcopy the direction that I want to copy from and that I want to copy into. And for that, I have to pass this flag CUDA memcopy kind. And the CUDA memcopy kind is just an enumeration, and the enumeration can take certain values. Like I can pass CUDA memcopy host to host, and when I do this, then the outcome will be just the very same as if I called memcopy on the host, like using the NVCC memcopy function. Like it's quite likely that CUDA memcopy in this mode actually just dispatches the whole call to memcopy, although this is of course an implementation detail, but the outcome is pretty much the same. And CUDA memcopy host to device allows me to copy data from the host to device, and CUDA memcopy device to host allows for the exact opposite. And then there's CUDA memcopy device to device, which allows me to copy from one memory region on the device to another memory region on the device. So, and when I use CUDA memcopy device to device, and assuming that I only have one device, so that I stay on this device, can be extremely fast, because this doesn't involve any host copies of the data, but it will just copy from one memory region to the other in GPU DDR memory. And the semantics of that function call are very similar to those of the NVCC equivalent memcopy, only that I have to pass this flag here that allows me to specify the direction of the copy. So let us just have a quick look at an example so that you get an idea how this would actually be used in a bit more real-world code actually. And for that, we'll again use our ZaxP example. And in the ZaxP example, we have this kernel here indicated by the global function. And the kernel takes 3 parameters, one scalar parameter and 2 pointers. And all those parameters will be copied into the kernel function by value. Like whenever I call a kernel, then the calling semantic is copy by value. Like I cannot just pass like a reference to the kernel. And therefore, I have to make sure that when I copy pointers into the kernel, that those are device-side pointers so that they're accessible from the device. Like there are actually other very special pointers, so-called managed pointers, that aren't so important right now. So suffice it to say that at the moment for us, those pointers that we pass in here are device pointers. So we cannot just pass host pointers in here and dereference them, because in the kernel we are on the device. Like when we dereference those pointers, we have to make sure that those pointers live on the device. So then I have a very simple host function here that will first, like I'm just assuming that there are already 2 arrays, hx and hy, which correspond on the host side correspond to those x and y vectors here. And I just assume that they are initialized to something useful. And then I'm allocating device memory, like GPU DDR memory, using CUDA malloc. And then I am copying from the host side pointers to the device side pointers. And I'm using the CUDA memcopy host to device flag here to indicate that we're copying from the host to the device. And then calling the ZaxP function, and for simplicity here, I only have one block here, so the example is fairly simple. And then I copy those pointers and also that scalar a, I copy them into the kernel using the kernel's parameter list. And then I have the kernel working on the vectors. And then I use CUDA memcopy again to get the data back from the device to the host. So in fact, when I use CUDA memcopy here, CUDA memcopy will also synchronize. Like the kernel call generally runs asynchronously in the stream, but that first call to CUDA memcopy here will perform a synchronization on that stream. Like we will discuss later what a stream actually is. These can be thought of as a queue when we were talking about the asynchronous host interface, but suffice it to say, CUDA memcopy will synchronize that stream so that when the CUDA memcopy function is called, I can be sure that the kernel returned. So then in the end, I have to free my arrays, like as I would have to do with host side malloc too. So in the next thing that we're going to discuss is shared memory. So this is this small on-chip memory regions that multiple threads in a block share, like when a block is executed on a shading multiprocessor. And depending on the architecture, the size of the shared memory is either 16 kilobytes or 64 kilobytes. And sometimes it is configurable so that a certain portion of the shared memory is actually devoted as L1. So if we want to use shared memory, we use this keyword shared, which is a device-side keyword. So we use shared to declare shared variables in our kernels, so on the device. And in order to use shared memory, we also have to allocate that shared memory. And there are two types of allocation. On the one hand, there is static allocation for shared memory. And on the other hand, there is dynamic shared memory allocation. And there are different syntaxes for either types of allocation. And when we use dynamic allocation, it's important to note that this involves the host. So we cannot just dynamically allocate shared memory from the device, from within the kernel, but we can only do so from the host. So the host can dynamically allocate shared memory. And we will now have a look at the two ways, like the static and the dynamic allocation. And when we better understand the mechanics of allocating and of using shared memory, we will also have a look at an example. So we will start with static shared memory allocation, and that involves only device-side kernel code. We're in a kernel here, and we're passing that kernel the pointer data. So this is a device pointer, a global memory pointer to GPU DDR memory. And then we also have that array shared ints here, and the array shared ints is a shared memory array, which is denoted by using the annotation shared here. And we're also statically allocating 64 ints. So now when we access shared memory, we usually use a pattern where we do the following. Like here we have this GDDR memory pointer, this device pointer, and in order to access the device pointer, we use the global thread index by computing it from the block dimensions and the block index and the local thread index. And then we perform an access into the shared memory array, and the shared memory array is actually accessed with the local thread index. And this is actually a quite common pattern where you perform a global lookup with the global thread index, and then you use the local thread index to index into the shared memory array. So what is important to note is that you have to synchronize all the threads in the current block so that they agree what is currently in the shared memory array. So whenever we perform a write access to the shared memory array, then we have to synchronize our threads. And what you also can see here is that when we want to fill shared memory, then we have to use the pattern that I just showed you here. Like we have to first allocate the shared memory, and then in the kernel we have to explicitly write to that shared memory. Like there is just no way to fill the shared memory other than doing this in the kernel and then using local thread indices or generally local accesses to the shared memory array. And this usually involves either computing something based on the local thread index, or it involves performing a global lookup into some global array. And then in the end we have to synchronize our threads. So this is static shared memory allocation, and then there's also dynamic shared memory allocation. And with dynamic shared memory allocation, we just omit this integer literal here, like we don't know in the kernel how much shared memory we'll actually use. And instead, we have the host performing the memory allocation by using the kernel configuration. And before, the kernel configuration was only comprised of passing the number of blocks and the number of threads per block. So basically the grid size. And with dynamic shared memory allocation, we additionally also pass the shared memory size so that the kernel later is able to initialize the shared memory array appropriately. So with dynamic memory allocation for shared memory, we have this syntax where the kernel call configuration is also used to pass the shared memory size in bytes, and then the shared memory is available in the kernel. So now that we understand how to allocate shared memory, let's actually have a look at an example where shared memory is put to good use. So in the classical motivating example for using CUDA shared memory is DGEMM, so dense matrix multiplication. And the example can also be found in the CUDA programming guide. And when I'm saying matrix multiplication here, what I mean is actually huge matrices, like matrices that have maybe a couple thousand rows and columns, so that this optimization actually pays off. And in general, codes that benefit from shared memory optimizations have a certain structuredness to them in regards to the memory access patterns. But on the other hand, the memory access patterns usually aren't exactly trivial. Like with the DGEMM example, as we will later see, we have those dot product operations where we have memory accesses that have different strides if we were to use linear arrays. So you usually assume that there is a certain characteristic to the type of memory accesses that are performed. And if those memory accesses are trivial, then we usually cannot benefit from using shared memory. And let's actually have a look at the DGEMM example and how the DGEMM example would be optimized using CUDA shared memory. So here's the basic idea of this. Like suppose we have our two matrices A and B, like this matrix A here and this matrix B here, and we want to multiply those two matrices, and this will result in a matrix C, which has the same number of rows and the same number of columns as either A and B. And when we perform our multiplication, like in a naive way, when we would use a CUDA kernel, we would devote blocks to a grid as follows. Like we would use a CUDA kernel, which would use blocks B1, B2, and so forth. And the threads in that block would be responsible for the rows of matrix A and the blocks of matrix B. And then we would have in each of those blocks, we would have a certain number of threads. And each of those threads in the blocks would be responsible for performing, and this is just the operation that you perform with DGEMM, would perform one of those large dot products. Like what you would basically have is you would have a dot product between this row of matrix A here and between this column of matrix B. And you would compute the dot product between those two in order to derive the entry in the result matrix C. So this would just be the naive way of implementing DGEMM, so matrix-matrix multiplication with CUDA. And the optimization that we will apply with shared memory will roughly go as follows. Like we already have this subdivision into blocks here. So what we will now do is we will break the computation up into blocks. And for that, we will allocate two shared memory arrays. Like we will be able to do this statically, because there's probably a certain size for that shared memory region that we can just use. And then we will process the two matrices in blocks as we did before, but we will do so by also breaking up the dot products into smaller portions, and those smaller portions can be computed in shared memory. Like we will first, during each iteration, we will fill the shared memory arrays by just having the threads copying all the data items that are associated with the block to the shared memory array A and to the shared memory array B. And then we will have the CUDA kernel compute dot products, but only over that small portion here, like not over the whole vector, but only over that part of the vector. So we will perform those smaller dot products, and we can perform those completely in on-chip memory, so all the memory accesses are on chip. And then we will compute the results of the dot product, and each and every thread will of course do that. And then we will add the result of that dot product to the data item in the matrix C here. So we have to make sure that we initialize that data item with 0, and then we will compute that dot product and then we'll add that to the data item in the result matrix C. And then we perform a synchronization, so we have to make sure that all the threads have finished that first block, and then we will move on to the next block, and then we will again copy all the data to the two shared memory arrays, so we overwrite the data from the last iteration. And then we will do this very same thing for all the threads, like compute that dot product and add the result of the dot product to the value that is already in memory. And then we will do so until we are finished and the whole matrix is processed. And you can already see the optimization here. Like, regardless of how you access memory, like there are two-dimensional arrays in C, but one of the two memory accesses here actually will have a stride that is quite high, like this, that has the same stride as the size of the column. So one of those strides here will be beneficial in regard to caches and to prefetching, and the other will be horrific actually, because we just jump in huge strides through memory and the prefetcher will just not work. And by using shared memory here, we're actually helping the prefetcher in a sense, as that we have that small cache memory region here, and we're basically telling it how to prefetch. Like, we're not like assuming that this here is the matrix where the stride is bad. And then we're basically telling the prefetcher that when we fetch the data item up here, that we're not going to fetch this data item and that data item and that data item, but that the next data item that we're interested in is the one in the row below. So yeah, we're basically implementing our own logic how caches are filled. And we'll now actually also see how this is done in CUDA code. So, and here it is. Here's the relevant portion of the CUDA kernel that performs DGEMM, so matrix multiplication on the GPU. And we are after the result that we're gonna write into this matrix entry at global thread index Y, global thread index X. So each thread is associated with one of those. And then we perform an iteration from left to right over all the blocks of the source matrix. And we're performing this iteration, and at the same time, while we're going from left to right, we're also going from top to bottom, if you recall the sketch from before. And while doing so, we iterate over each of the blocks, and then we just obtain like a pointer to the data for each of the submatrices that are associated with the block. Like, I'm just assuming here that you can, like, this is a global memory pointer, and the global memory pointer allows us to access the submatrix for the block that we're currently interested in. And then we're statically allocating memory that can hold enough data items to store the submatrix, like the two submatrices A and B. And before we perform any actual work, we have our threads copy from global memory to shared memory. Like, we take that global memory pointer that we obtained before and copy all the data from that submatrix to our shared memory matrix. So when we've done that, after all the writes have finished, we have to synchronize our threads. And then we have a for loop that iterates over the block size and computes the local dot product. And by that, updating this result variable CV. And then finally, we synchronize our threads again. And when we're done, like when we're iterated over all the blocks, we assign the result in CV, we assign it to the result matrix entry that we have been working on. So we use a 2D grid for that, and we perform an iteration over the number of blocks that we subdivided the source matrices into, copy our submatrices into shared memory, which is associated with the block, and then we perform local dot products. And whenever we start computing a dot product, or when we finish computing a dot product, we have to synchronize, because we perform write accesses where the threads have to agree upon what data is actually in the shared memory buffers. So here's just this same illustration from before, where you can see all that again, like with our blocks and with our shared memory arrays and with our local dot products that are computed. And you can see the warps that operate on those blocks. And you can play around with this example. The DGEMM implementation of CUDA is actually part of the CUDA samples. So you can play a bit with that, and you can also try to figure out how much faster it actually is. And with that, we're at the end of today's session. Like we discussed, we discussed a lot of code today. And we will continue to do so in our next session, where we hopefully finish our discussion of the CUDA API. And from there on can transition to an actual application where GPGPU is used to sort data. See you then.